by straightening it out. Now, the same thing for surfaces. I'm going to assume that I can flatten them out and parametrize them using that flatten out thing. And then there would be a one-to-one relationship in there. But you've been doing this for a while, you just don't remember it. A bunch of these things for a while, and you don't remember them a whole lot. So this story is, who can remember this from from chapter 15? When did we see this in chapter 15? What's that? No. In chapter 15, what concept did we see this picture for? Anyone? What's that? What was the thing that had Jacobian? Transformations. Everybody remembers this picture from transformations? Do you guys remember transformations they were always either from R2 to R2, transformations, either R2 to R2 or R3 to R3. Who can tell me with parametrization if that's true or not? What are the parameters home? Is parameter home R2 or R3? 2. How about the surfaces home, R2 or R3? R3. For parametrization of surfaces, you go from R2 to R3. Everything else is the same. Even you compute the Jacobian in there, right? So it's sort of, a lot of times you computing some sort of a Jacobian for that. Okay, so that's the start. So a parametrization G from R2 to R3 takes two parameters U and V using three functions, X, Y, and Z. X and Y and Z are all functions of U and V. Do you guys remember what transformation was for this? So in transformations, if I had three items there, I would have G of U and V. My friends, today is not the day to chat. This was the transformation, right? You would have 3 on the left side, and you have 3 on the right side. But now that you have parametrization, only has 2 on the left side, and you have 3 on the right side. The other thing that I want to say is a lot of times they are very similar. To make this work, make that one work through that, you just have, you set one of these 3 a constant rather than a parameter. And it would work beautifully. Fair game? You're ready to set things equal to constants? Apparently not. There we go. No answer was given. So let's go through a few of these. Does this look like a parametrization? Can anybody guess what kind of parametrization is this? Why am I asking you to guess? Because look at this. What's the x value for the parametrization? What's the x value? X value is 2 minus 2u plus v. Is a linear functional of u and v. Oh, that's linear. What is the y value? Oh, sorry, I went too far. That's the y value. Linear or not? Yes. How about this one? Linear again, correct? I gave you the answer in here, but imagine, what is linear in 3D? Plane. So what is the linear surface in 3D? Plane. So you sort of know if I see this linear relationship, it has to be ending up to be a plane. Now let's go to the next one. What is happening here? What is the x value? U, first parameter. What is the y value? V, the second parameter. What is the z value? Function of it, u and v, right? It's function of x and y. What do you guys guess this is parametrizing? Let's see. So it says x is equal to u, y is equal to v, z equal to f of u and v, right? Let's eliminate u and v, see if we can get anything. How do I eliminate u and v? I get z equal to f of x and y, correct? So that's the surface, that's a graph of a function. Fair game? So I eliminated u and v between the between what? X, y, and z. And I got that. Fair game? We're good? So now the next thing. Who knows this one? I'm expecting everybody to know. Sphere. Why did you say sphere? What's that? It says spherical coordinates, but there's one more item in there. What is special about a sphere? What is constant? Radius is constant. Is the radius here constant? Yes, how do I know radius is not a parameter here? Because, look at this, theta is a parameter, phi is a parameter, r is not a parameter. Therefore, r is a constant. R equal to a constant. You guys are taking pity on me. I appreciate that. Sphere. I'm starting to take pity on myself. So, no? It's bad? Okay, okay. Okay. So, I mean, the rest of them are not as important. I do want to say something. So the next one, do you see that I replace R by what? A, B, C, right? It's not the same thing. When you change in X, that constant in X, Y, and Z direction, you sort of stretch or shrink in the sphere in different directions. So you end up with an ellipsoid. Fair game? Now, the last one is very difficult to guess, and I'm not asking you to guess. It's going to be a Mobius strip. Have you seen the Mobius strip before? So you turn it around, and it goes back if you guys, when I'm not as germy as I am now, I make a bunch of them for the class so you guys can try it. When you go around the Mobius strip and with a normal vector, you sort of end up in the opposite direction. So I'm going around. Can you guys see this? Do you see this? I started from the opposite one, right? Now I ended up here. Mobius strip doesn't have inside or outside. It doesn't have an orientation, as we are going to discuss. So Mobius strip is not something we do in this course. It's not something that are important for the regular lower level physics and engineering courses. It's something to understand why what we do in this course is important. This condition that we have in this course is important because we need to have orientation in this course. This one doesn't have an orientation. I'll make you a good one next time. Make you a bunch of good ones. Wash my hands, I create a few. I'll bring it to class. Okay, so again, the whole lot of them are similar. Transformation and parametrization seem to be very similar. There's a little bit of like, yeah, it's onto the shape. It's just being a little nitty-gritty. The most important difference between the parametrization and transformations is this. One goes from R2 to R3. The other one, it could be going from R2 to R2 or R3 to R3. So that's the biggest difference, basically. So now I'm going to wave my hands and then explain a few things. Oh, no, not yet, not yet. I haven't done any examples yet. So when you're basically, you're taking a little piece of rectangle in the parameters home, you basically stretch it, push it, distort it in somehow into another surface. That little piece of paper has grid lines, and those grid lines are going to stretch with that shape. Okay, so remember that. And so a lot of times when you're parametrizing the same parametrization that does the surface actually defines a parametrization on each line of the grid line. How? By setting, let's say, in here, what is the blue grid line? U equal to constant, right? So if I have U equal to a constant, then I plug it into G of U equal to a constant and V, then this is going to give me basically a parameterization of one variable because that's a constant. A constant. So this G not only takes the entire piece of a plane to a surface, it takes all the grid, each grid line to another grid line in the other one. Each curve in here goes to another curve in there, basically. Fair game? So that said, a little bit about that. Now, we discussed this in the very beginning. One way, if you have a graph of a function, one way to parameterize the graph of the function is this. You just set your x and y to be the parameters. So set x and y to be parameters. And then g of x and y as x, y, and f of x and y is a parametrization. I think I missed to explain this. Do you guys see my notation G has an arrow on top? I'm emphasizing the output of this function is going to be a vector, not just a scalar, right? Every time I write G with a vector on top of it, I'm emphasizing that. It just feels like, can you guys tell that the graph of the function looks like I push the domain of the graph up, right? With all the grids pushing up and kind of getting stretched in some ways or another, or getting shrunk in one way or another. Can you guys see this being stretched up? So what is happening is that basically, eventually, not right now, and toward the end of today, I'm going to start talking about every little rectangle in the grid function goes to another little rectangle over there in the surface, and there is a rescaling factor in the area that we're going to compute. It's going to be very close to the Jacobian. In some way, it is a Jacobian, but not in the definition of our book. In our book, it's not defined as Jacobian. We don't define Jacobian very generally. We define Jacobian very locally in this book. And that serves us the best. It's the best way to teach a first course in multivariable functions, basically. But there's more to Jacobians, basically. OK, so now I'm going to give you one example. You guys do. Quickly answer. And I'm not trying to come upstairs. I'm sorry. What's that? What's the answer? No. No. So how many? Yeah. So, yeah. Mm-hmm. You're just parametrizing it. Look over there. You're writing it right to that. Okay. Sorry, guys. I'm not going to come upstairs. I'm not going to come walk between you guys. What I want you to notice, it's a graph of a function. You're parametrizing. You're parametrizing a graph of a function. So what do? You can take x to be the first parameter, y to be the second parameter, and then f of x and y to be the z value. Fair? Everybody okay with that? What's happening, Alyssa? Did you figure it out? Okay. Can I count down? 4, 3, 2, 1, 0. What's the answer? Okay. Now, do you guys remember how much emphasis we put in when we parameterize a line segment? Everybody remembers that? How do I parameterize a line segment? So first point, right? First point plus t times a vector between first point and the last point. Why did I do that? Then I can use t between 0 and 1. And I start from the beginning point to the end point. Now, of course, parametrizing plane I can do multiple ways. I could have basically for any parametrizing planes, for any P on the plane and vectors A, B on the plane. Apologies. Such that A is not parallel to B, I can parametrize the plane using this. G of U and V is equal to OP plus U times A plus V times B. Right? So give me two vectors that are not parallel. Let's say 2, 3, and 1, 5, 1, 0. And a point. This gives me a plane containing zero, 1, 0, and parallel to so that's all you need to do. Two vectors that are parallel or within the plane, and you go. But then this causes problem if you have, what is the equivalent to line segment? Let's say line segment to line is equivalent to what to plane? Can anybody tell me? Line segment to line, what to plane? What's that? What, a finite thing. Think of a finite thing in a plane. How do you draw a plane? Like that? There is a reason. This to a plane, that parallelogram to a plane is kind of equivalent to a line segment to a line, right? That's a finite thing, right? Fair game? No? What's that? Segment, I'm saying a field parallelogram, right? A parallelogram too. So no, there's no special name. Sorry, that was. So now I'm going to give you another example. Ready? Before giving the example, why did I say this? Look at the vectors A and B. Do you see what happens here? I'm multiplying vector A by 2, so U is 2, V is 1. You get this size of the vector. It's just summation of that 2 times A plus B is going to be that. Let's do, if I do A times 1 plus 2 times B, that's the vector that I get, right? Can you tell that I can pick any point, and then I can write that point within this plane as a multiple of A plus B, multiple of B? that's a fair game. So that's why I can actually parametrize plane the way that I said it, if that makes sense. Now I want to do this example. I'd like to parametrize a parallelogram this time. And let's take a look at the difference. Before I parameterize the parallelogram, I want to draw the parallelogram. Let's draw this parallelogram. Do you guys remember from the beginning of the class when we drew these parallelograms? What is P? P is 0, 0, 1. 0, 0, 1 is right here. Then Q is 3, 0, 1. 1, 2, 3, and it's around here. 3, 0, 1. Then I have R, which is 3, 2, and 0. And then I have S, which is 0, 2, and 0. It didn't come out very parallelogrammy again. Almost. There we go. So that's a parallelogram that I have. So if you want to parameterize the parallelogram the same way you did the line segment, start from a point. Which point should I start? Should I start with P? Let's start with P. Start with P. Draw two sides of the parallelogram draw two vectors to the two sides of the parallelogram. Do you see that? So I have, what is that? I have PS and PQ. Agreed? So what is PS? PS is equal to 0 to negative 1. PQ is equal to 3, 0, and 0. Agreed? Okay. Now, all you need to do, again, for plane, you don't have to be so careful. But if it's a parallelogram, you have to be more careful. Because you want to make sure that all the points that you parameterize, you want to have a bounds for the parameterization. And to have a nice bound, you could do it multiple different ways. The bounds are not going to come out nicely. But if you follow this step, start from a point, draw two vectors that are sides of the parallelogram. Starting at P. Then this parameterization, what was P? Plus, what was PS? What was PQ? This is OP, PS, PQ. For U between 0 and 1 and V between 0 and 1 parameterizes every point on the parallelogram. Okay. Questions? So what did I do? I started from a point, drew two vectors that are side of the parallelogram. If I draw any two vectors that are not found in this way, like if I had chosen this vector and that vector, then the parameters, the bounds for the parameters would not be 0 and 1. Any other way, U and V are not bounded by 0 and 1. Almost any other way. So it could be, some of them are okay-ish, but overall it's not bounded by 0 and 1. This is the way that you bound it by 0 and 1. Fair game? So does this make sense? Let's go back to this picture again. First of all, this is the actual picture of what I did. It's a nicer picture because my drawing are not the best, obviously. So I have this picture. But let's go back to what we were doing a little bit earlier. Look at that. It just seems when, if I want to stay on a parallelogram made by the two vector A and B, right? If I want to stay between on a parallelogram made by A and B, which is a small one down here, I have to have U and V between 0 and 1, which makes sense. That's how we did it over here. Fair game? It makes more sense if you had Math 290. It's a little bit more sensible if you had Math 290. But that's how actually works. Could I have used this to parameterize? Yes, I could. I could have had x, y, and then solve for z to parameterize. An equation of the plane that you already knew. That's another way of parametrization. Yes, but then x and y, you have to find the bounds for x and y also. So now my question for you. So what point are you starting at? P? How do you know it's P? That's the one that doesn't have any parameters next to it, right? P by itself, or P is by itself, right? So point P. Point P is down here. Now I have S times PQ plus T times PS. PQ is right here. What is S? What's the value of S in here? 0.5. What's the value of T here? 0. So I'm going to go PQ times 0.5. So 0.5 times PQ, what would that make the P? How long of the, no, wait. Start from here. Add half of this length. Where do you end up? What? Did we get it? Is it too easy? So start from P, and then add half of the PQ, which is, because 0 times PS means you don't have anything on that direction. 4 3, 2, yes, 1. What is the answer? Yes, it is B. Why did I say C? M, it's right there. That's the point, right? That's the point. 4, 3, 2, 1, 0. Okay, so now, how do we parameterize a cylinder? Anyone? Parametrization is like transformation. What do you use? What transformation do you use for cylinders? It's coming with the name. What? Cylindrical. So what was the cylindrical parametrization? So you would, Jacobian was R. Remember that. So you had G of in transformation. You had G of R, theta, and Z. Agreed? Can I have G of P parameters? No. What am I supposed to eliminate in this case? Radius. I have to eliminate. Because R is equal to C. So this would have been, you guys remember this, right? Do you remember that transformation? Now all I'm going to do is I'm going to eliminate R. Now this is the parametrization. And what I get is C cosine theta. Make sure that what you're eliminating as constant stays constant. See, I wrote C instead. Now, can you guys tell me the bounds? Theta 0 to pi. And what else do I need bounds for? Z. 2 parameters, 2. And in this case, it seems like it doesn't seem that it has actually a bound because it doesn't define any bounds. So I'm going to assume that Z is in R. Unless a restricted bound, restricted, is given. So like this is just a piece of theta Z that goes to this piece of the cylinder given. Fair game? Surface of the cylinder, not a field cylinder. We're good? Questions? None? Okay, a quick question. Do you see this little rectangle? Right? Not this early, darn it. This little rectangle, I can transform it into this shape, right? As a cylinder. So the only difference in here is that if I cannot start from 0 to 2 pi to do that transformation. If I start from 0 to 2 pi and go to the cylinder, then there's some stretching happening. That's why you need a Jacobian. Because remember, this piece, this length is not exactly the circumference of the circle in here. It's smaller. And so we basically multiply that by r to make that stretch that is happening going from here to there. That's where Jacobian is coming from. Did that make sense? So it's really, if it was exactly the same area, surface area, and I was going to just fold it into a cylinder, I wouldn't need that Jacobian. But because there's a stretch happening in there, you will need the Jacobian. Okay. Yeah. Your turn. Yeah? They're good questions. I am very slow today. I don't know why. No? Everybody's tired today. Me too. Yeah. What's that? I heard that. Sorry about that. Yeah. Nick, be kind to them. That's not. Kindness is your motto. Gabe, don't tell on Nick. Did you ask me a question? No? No, you're okay? Okay, so what? Okay, so I have one more of these. Do you want to do the next one and then I lecture a little bit? Watch the video if you're going to physics. Okay, let's do the two of them quickly. So what is the answer to this one? Hold on. What kind of transformation would you use if it's sphere involved? Spherical? So spherical. Spherical has how many parameters? 3. One of them I have to set constant. Which one is that? Radius. What is the value of the constant value for radius? C. Which one of these reflects radius being C? Did everybody get that? Which one is it? 4, 3, 2, 1, 0. Okay. What I want you to do here is to eliminate what are the parameters here? Can we do this quickly? Either stay or go quickly though. That's not committed. What is the sign? Should I stay or should I go? So, okay, a little faster, a little faster. Now, my friends, the position in here is a parametrization is given to you, correct? A parametrization is given to you. I want to know what surface that is. What I do, it's the same thing that we did with curves. I eliminate the parameters. What are the parameters here? Theta and u, correct? Theta and u. Can anybody tell me how to go about eliminating parameters here. Which one would you eliminate first? You want to eliminate u first? Okay, so, oh, by the way, this is the wrong problem. Shoot. So I want to eliminate u first. So what do? Solve for u in which one? C equal to square root of u squared minus 1. So I get u squared is equal to, agreed? Right? And then what do I get for u? Now what do I do with this? Give me some ideas. How do I eliminate sine and cosine, typically? If I square, go to power 2, what do I get? Now what should I do? Now add them together. What do I get? Yes. So what's the answer? 4. Why didn't 3? They should have tried. 2, 1, 0. Which one is the answer? Oh. They left. Okay. So, what's that? No, that's kind of mean. That's kind of mean. Okay, can I do, how much time do I have? Do I have 1 minute? No. God, this is getting very stressful. So, what the next thing that I want to do is actually tell you how to go from parametrization to surface area. Can you guys guess what happens in surface area? You have a small area in the parameter space, and then it morphs to the surface the same way it did in transformations. So what do you need? You need G sub u and G sub v. So if you have a little area over here, delta u times delta v, then delta u times G sub u gives you the stretched out vector. Delta v times G sub v gives you the stretched out vector in the other direction. What gives you the area element? The magnitude of, who said cross product? No one? Cross product, the magnitude of the cross product, which is exactly what we're going to do example next time. I'm not going to go over it. Okay, see you guys. Bye. Over there. Let me put mask on when I'm talking to you now that I'm up close. She's right there.
Okay. I wanted to ask you something.
Okay.
I'm sorry if I got you sick.
No, I don't think you did. I actually was in a class to observe, and the graduate student was